This is the second part of section 3.1 exponential functions. And in this lesson, we're going to start modeling exponential functions given some data. First, we want to look at what is a growth factor. So if we look at these two functions, we have f of x equals 2 to the power of x, and g of x is equal to 4 to the times 3 to the power of x. And so in the example, it asks us to determine what number is being multiplied to each y value. And I have already pre-filled this. But if you notice here, from 1 to 2, I would have to multiply 1 times 2 to give me 2. 2 times 2 would give me 4. 1/4 times 2 would give me a half. Half times 2 would give me a 1. So all the y values here are being multiplied by that same number 2. And in this table, we have from 4 to 12, I would have to multiply 4 times 3 is 12. 12 times 3 is 36. 4/3 times 3 is 4. 4/9 times 3 is 4/3. And again, the y values here are being multiplied by the same number, 3. The number that's being multiplied is always going to be the variable b in the equation y equals ab to the power of x. And this number b is what we call the growth factor. And so if we look at example 7, it says, model the data using an exponential function f of x equals a to the bx. So the first thing we want to do is figure out what a is. Remember that a is your y-intercept. So if you notice over here, at x equals 0, we got 4. And so 4 is your y-intercept. That represents what a is here. So in this example, 4 is going to be your a. So my y-intercept here is going to be 0 and 10. And I know this is my y-intercept because the value at x equals 0 is 10. And then we need to figure out what b is. In order to figure out what b is, we want to ask ourselves, we want to look at the y coordinates, and these are the y's here. And so in order to get from 10 to 40, I would have to multiply by 4. 10 times 4 is 40. And 40 times 4 would give me 160. So in this example, b is going to be 4. So now we just write the equation. So my equation here, using y equals a times b to the x, is going to be a, which was 10, b, which is 4, raised to the power of x. And that's our equation. So let's look at example 8. Our a here is, our y-intercept is 0, 160. And then for b, notice that here we're going from 160 to 40. So we can multiply 160 times 1/4, 40 times 1/4. And so 160 times 1/4 gives me 40. 40 times 1/4 gives me 10. So if I'm multiplying, then my b here is going to be a 4th. Some of you might have seen it as dividing. 160 divided by 4 is 40. 40 divided by 4 is 10. If you use the word divide, or if we divide, then in this case, b is going to be 4. Now the equation for the multiplication side, we get y is equal to a, which is 160. b is 1/4 to the power of x. And for the division part, we would have y is equal to 160. b is 4. However, since we are dividing here instead of multiplication, we're going to represent this as a negative exponent. So if you notice, this equation and this equation are exactly the same, but one is written with a positive exponent and one is written with a negative exponent. Okay, let's try one more. So here we have Our y-intercept is 0, 500. And b, we're going to be 500 times 2, 1000 times 2. So b is going to be 2. So my equation would be a, which is 500. B is 2 to the x power. Okay, so we're not always going to be given a table like this. And so our next example is going to help us to still come up with the equation. So the first step in writing an exponential curve that passes through the points 1, 6, and 324 is going to be the following. So first we want to substitute the points into the equation. Y equals a b to the x. So I'm going to let this be x and y and this x and y. So what we would have is, for the first point, I'm going to have 6 is my y, x is my 1, and then the second one, y is 24, and x is 3. So for this step, this is what I get. Again, I'm using this equation here. For step 2, we're going to divide one equation into the next equation. To make things simpler, always make sure that in your numerator you use the highest exponent. So in this case, the highest exponent for b is 3. And I'm going to divide this by my other equation. Okay. And then step 3, we're going to solve for b. Okay, so in other words, we have to simplify this equation to get our b. So I'm going to rewrite it. Okay, so this is going to become 24 divided by 6 is 4. My a divided by a is 1. B cubed divided by b to the first power would be b squared. Okay, so now we can solve for b here by taking the square root. So I'm just going to rewrite it again. I can take the square root on both sides. So b is going to be plus or minus 2, but we're only going to look at the positive values for b here. Okay, so b is 2. Step 4 is to substitute the value of b that we found in step 3 into one of the equations and solve for a. And at this point, you can choose either equation. You can choose this one or this one. I'm going to go ahead and choose the first one. Okay, so here we're going to substitute what we know. So we are going to have 6. B, we just found out, is 2. And so I'm going to solve for a. So a is going to be 3. And the last step is write the equation using the values for a and b. So my final answer here is going to be y equals a, which is 3, times b, which is 2, raised to the power of x. And so that would be my equation. So let's try example 11. So here I just always start by writing our general form 2 times. This is x, this is y, x and y. So for the first one, I have negative 4 is equal to a, x is 2, And then the next one is negative 16, and x is 4. I want to divide them using the highest exponent of b as my numerator. So negative 16 divided by negative 4 is 4. My a's become 1. B to the 4th divided by b squared is b squared. Solve for b. Take the square root here, so we get b is equal to 4. We need to substitute our answer into one of the two equations. I'm going to go ahead and use the first one. So b is, I'm sorry, this should be a 2. So b is 2 squared divided by 4. So a is negative 1. So my equation here is y equals negative 1 times 2 to the x power. And let's move on to the next example. Same idea. Y is equal to abx. Y is equal to abx. So here, the first one, y is 2, and x is 1. Y is 6, and x is 4. So if I divide, 6 divided by 2 is 3. B to the 4th divided by b1 is b cubed. I can take the cube root on both sides. So b is going to be equal to the cube root of b. So if you put this in your calculator, we would have 1.44. I'm going to just round to 2 decimals. If you enter it in your calculator, make sure that you're using parentheses. So for example, on my phone calculator, let me bring it up, I would enter 3 raised to the power of the cube root. I don't have that symbol on my calculator, but I know that a root can be written as a fraction, so I can say 1 divided by 3. And so I get 1.4422. I'm going to round to 2 decimals. Once you have your b, then we need to plug it back in. I'm going to use the first equation. So I'm going to divide by 1.44. And that comes out to 1.39. So my equation is 1.39 times 1.44 to the x power. And let's go on to page 80. So now we can see how we can model data in real-world situations. So the first example is on bacteria. It says a bacterial culture starts with 1,000 bacteria and doubles in size every 3 hours. Find the exponential model for the size of the culture as a function of time t and hours, and use the model to predict how many bacteria there will be after 2 days. So remember, when a problem asks for a model, they're really asking for an equation. That's just another word for model. They also tell us that this is exponential. So that means that we're going to need to be working with an exponential function. Sometimes they want a linear function, a quadratic function. In this case, they want exponential. And so the previous examples that we were looking at, they all required us to have some values. So for example, in order to do these equations here, we always needed some points. So notice here I at least had 2 points. So in this problem, they don't give me that information. So we need to get it from what is already written in the problem. So whenever you start something, we're starting with time 0. And at time 0, you start off with 1,000 bacteria. So you notice here my 0 is going to be the time. And the 1,000 is how much bacteria I have. So then it says that it's going to double in size every 3 hours. So at time 3, this is going to double. So instead of 1,000, it's now going to be 2,000. So we can follow the procedure now since we have 2 points. And you're going to notice that this value 1,000 is actually already the value for A. Because notice that x is equal to 0, so that makes this the y-intercept. But if you're not sure or you want to follow the process, then we can do that as well. So y is 1,000, and then x is 0, y is 2,000, and x is 3. So if I divide, then we're going to have 2 is equal to b cubed. Take the cube root. So we end up with b is equal to 1.26. Now we need to find a, so we can substitute it back. I'm going to go ahead and use this one here. B is 1.26. Remember that anything to the 0 power is always going to be 1. So A is 1,000. So again, from the beginning, this is already going to be A since you have x equals 0, so that's your y-intercept. So your model or your equation is y equals A times B to the x power. Once we have a model, then we can predict how much bacteria there will be after 2 days. So it's important here to know that your time is in hours. So note it says 3 hours. So this is hours. And the reason it's important is because now they want us to predict after 2 days. Well, how many hours is in 2 days? So that's going to be 48 hours. And so now I can use my model and substitute that information. So for x, I'm going to put 48. And so in the calculator, we would type in 1.26 raised to the 48th power times 1,000, and this will become the following. So this is how much bacteria you would have in 2 days. Okay, let's look at example 15, aspirin. After taking an aspirin, a patient has observed 300 milligrams of the drug. If the amount of aspirin in the bloodstream decays exponentially, with half being removed every 2 hours, find the amount of aspirin after 5 hours. So again, we need to have 2 points. So my first point would be 0 and 300, because that's what I began with. And then it tells us that the aspirin decays exponentially with half being removed every 2 hours. So after 2 hours, we're only going to have half of the 300, which is 150. Again, I always like to make a note of what my x is, the unit for x, which is hours in this case. I'm going to also say that this is already A because that's my y-intercept. And so really, I can just plug that information. So here, I'm going to use my second point. Y is 150. A is 300. We don't know what B is, and X is 2. So if I divide by 300, I get B squared is equal to a half. Take the square root. So b is going to be equal to 0.7071. So my model is going to be y equals a times 0.7071. Notice that since this is decaying, that's why we end up with a decimal here. So it says find the amount of aspirin after 5 hours. So it's asking for 5 hours. My units are hours, so I can just plug in the 5 for x. And so that's going to become 53.03. Since you're working with a word problem, then it's always nice to write a sentence. So after 5 hours, there is 53.03 milligrams of aspirin left in the bloodstream. Okay. So now let's look at an example of what's happening today. So we have the COVID-19 that's keeping us in our homes. And so what I did is I looked at the real time tracker here. And if I hover my mouse over this, it tells me that on March 13th, I had 1 case. And April 5th, I'm up to 115 cases. So I took that data and I just wrote it down as a little table here. Okay. So notice here is the date. The top number is the date. And then the number below the date is how many cases exist. So if I look at this data, in the first weeks, it was growing a little bit slow, and then now it's increased in growth. So I'm going to choose 2 points, and I'm going to pick, let's see, I'm going to pick this number here, and I'm going to pick something that is kind of double, so maybe this one here. Okay, so this number here is times 0. So I'm going to label these as days. So this is the 12th day here. And that's the 16th day. So I'm going to get 2 points here, 12 and 21, and 16 and 40. So remember, this is my day, this is the number of cases. So I can model doing what we just learned. And so if I plug in what I have, and I divide, then we're going to have 40 divided by 21 is, let me put it in my calculator, 1.904761, 9048. I want to keep as many decimals as possible. 16 divided by 12, or b16 divided by b12 is b to the 4th power. Or you could have just left it as a fraction. It's up to you. And so if I take the 4th root, then we're going to get the following. So I'm going to use 1/4. So b is 1.17479. So you can keep as many decimals as you like, but the more decimals the closer your prediction will be. Okay, so that's my B. Now we need to find A. So I'm going to use this equation. And B is 1.17479 to the 12th power. So if I raise that to the 12th power, I get the following. And so I'm going to divide 21 divided by that number, 6.910,713,5693, and that comes out to 3.0388. So my model here is going to be 3.0388 times B to the x power. So we can use our model to make a prediction. So let's say we have, so that was the 16th day, 17, 18, 19, 20, 21, 22, 23. So I'm going to plug in 22 into our equation to see how close we are. So we have 1.17479. So here I'll put it here. And we're going to raise that to the 22nd power. So that gives me 34.603 and so on. And I'll multiply that times 3.0388. Oops, hold on. I accidentally pressed it twice. So 1.17479 raised to the power of 22. That's 22 days since this began here in El Paso, times 3.0388. And so Y would be 105.15. So if you notice, on day 22, we actually had 106 cases here in El Paso. My equation is predicting 105.15 cases, which is really 106, since we can have 0.15 of a person. And so if you wanted to know how many positive cases will there be in 40 days, for example, let's figure that out. So we can use our model, 1.17479 raised to the power of 40 times 3.0388. So in 18 days from now, if we don't practice social distancing, etc., we might be looking at 1,910 cases. Okay, so this is an example of how we can use math to make predictions. Okay, so let's move on here. One of the things that we want to do when solving for exponential functions is we want to be able to solve for the variable x. And the variable x it's hard to solve for whenever it's an exponent. And so here, if we have this, for example, 8 equals 2 raised to the power of 2x minus 1. then that becomes difficult because the x is an exponent. So we can use what we call the one-to-one property. And basically what the one-to-one property tells us is if you have, for example, a raised to the n power equal to a raised to some other power, then since the two bases are the same, the a's are the same, the bases, then we can say that m is equal to n. Okay, so that's the one-to-one property. So in this case, the base is 8, and then we have a base of 2. They're not the same, but we can rewrite it so that they are the same. So 8 can be written as 2 cubed. So 2 times 2 is 4, times 2 is 8. So notice now they're the same. So using the one-to-one property, I can say that 3, the exponent, is equal to the other exponent of 2x minus 1. And so by doing this, now x is no longer an exponent, and I can solve for x. So I'm going to add 1 on both sides, divide by 2, so x is going to be equal to 2. Okay, so let's look at letter B. Here we have 1/3 and 27. They're not the same. We can try to rewrite them. So 27, I can rewrite it as 3 cubed. 3 times 3 times 3 is 27. And now the 1/3, we want to write it as a positive exponent, or we want to write it so that the base is 3. So I can write this as 3 to the negative 1, and then I have negative x. So this here is going to be 3 to the x is equal to 3 cubed. So x is going to be equal to 3. Let's go to 81. So the natural base e is equal to 2.718, and it goes on forever. And the function f of x is equal to e to the x is called the natural exponential function. So in your calculators, you should have a scientific calculator. So in mine, you can see it here, it's e to the x, and it's always going to be close to the ln and the log. Okay, so it says use your calculator to evaluate f of x equals 40 e to the x at each value of x. So I can write this as 40 e to the 0.3. So in my calculator, I would enter e to the 0.3, and then I'm going to multiply that times 40. Okay, so we get 53.994. And for this one, we get so I'm going to have e, and we have negative 1.2 times 40. And you can round as many decimals as the problem asks for. And then the last example here has to do with compound interest. And so here, if we have compound interest, the formula we want to use is a equals p 1 plus r divided by n times nt. So a is your final balance. P is your principal, in other words, what you begin with. R is your rate. And N is how it's being compounded. And for that, you can have different options. For example, if they say quarterly, we would use 4. If they say monthly, we would use 12. That means every month. And yearly would be 1. You could have weekly, you could have different compounding periods. And then the T is for time. And then for continuous compounding, we would use the formula A equals P ERT. A still stands for final balance. P is still your principal, your beginning balance. R is your rate, and T is your time. E is just your natural number, E. And so here we say find the balance A when 2,000 is invested at 2.1% for 10 years, compounded n times. So what I like to do is write down the variables. And so here they say find the balance A when 2,000 is invested. Since we invested 2,000, that's what we begin with. The rate is 2.1%. I'm going to write it as a decimal. N is how it's compounded, in this case 4, and it's going to be done for 10 years. So we plug this into the formula. And we solve. So 0.21 divided by 4 is going to be 0.00525. 4 times 10 is 40. 1 plus 0.00525 would be 1.00525 raised to the 40th power. So I'm entering that into my calculator. And so I get 1.23330005519. I'm going to multiply that times 2,000. So my ending balance is going to be 2,466. So for the next one here, A is still A, P is 2,000, and the rate is 0.021 times T, which is 10. So we evaluate 0.021 times 10 first, and we get 0.21. So now you want to do E raised to the 0.21 times the 2,000. Okay. And finally, the last example here, I'll give you a chance to work on it. If you have any questions, you can send me an email. So I'm going to put a star here, which means for you to try on your own. Stay safe out there.